A very warm greetings to all. So, I am Dr. Muthuselvi, Professor in the Department of Information Technology, Kamaraj College of Engineering and Technology. So, today we can discuss on deadlock deduction algorithm. So, this is an example for a traffic deadlock. So, 4 roads are there and the vehicles are standing like that, and there is no scope for further movement. So, this is what we call traffic deadlock. Similar to this one, in computing system also there is a possibility of having deadlock. Let us see what is that. So, let us assume we have set of processes, and each and every process it is having one resource. Suppose one resource it is required by another process at the same time, and the process is yet to complete. Then the other process it has to wait for the resource. So, now we can say there is a deadlock. So, here the processes they never finish executing, and here the system resources they are tied up so that the jobs they are prevented from starting. So, one example, suppose I have a system of 2 disk drives, then P1 and P2, we have 2 processes P1 and P2. Suppose P1 is holding one disk drive and P2 is having another disk drive. So, both requires both the disk drives. So, in that case P1 is not able to complete its work because it needs one more disk drive. Similarly, P2 is also not able to complete its work because it is also requiring the other disk drive which is actually used by P1. So, now there is a deadlock. So, generally we have the system model like this. So, in a system we are going to have many resources, and let us say the resource types are R1, R2 up to Rm. So, the resources actually they may be the CPU cycles, memory space or IO devices, all these are resources, and each and every resource has Wi instances. There may be more than one instance for any resource. So, each process actually utilizes a resource in the form of request, use or release. So, sometimes the system actually there we can find whether there is a possibility of having deadlock. So, using that we can prevent the deadlock or a deadlock avoidance, we can avoid the deadlock, but at one particular time the system may not be able to find out the deadlock or it may not be able to avoid the deadlock. So, automatically it enters into the deadlock. So, here there is an algorithm to examine the state of the system to determine whether a deadlock has occurred, then to recover from the deadlock. So, it is required to detect the deadlock. So, in when we are discussing the deadlock detection, a system with single instance of each resource type or the system may be with several instances of each resource type. Suppose we consider the system with single instance of each resource type. So, here we have to know all resources are with the single instance. We can use a wait for graph, in short WFG. So, it can be used to define deadlock deduction algorithm. So, this WFG it can be obtained from resource allocation graph, where in the resource allocation graph we will have the processes and the resources connected. Suppose we are going to discuss several instances of a resource type. So, here we have to focus on 3 important points: available, allocation and request. What are they? Let us see available. So, it is a vector of length m, indicates the number of available resources of each type. Allocation, it is a n cross m matrix. So, it defines the number of resources of each type which are currently allocated to each process. Then request, it is also another matrix of size n cross m. So, it indicates the current request of each process. So, if request of I comma j is equal to k, then process Pi is requesting k more instances. Now, let us see the deduction algorithm. The first step, work and finish are the two vectors of length m and n respectively. So, initially we are going to assign like this, work is equal to available. Then for I is equal to 1 to n, if allocation is not equal to 0, then finish of I is equal to false. Otherwise, finish of I is equal to true. Then the second step, we have to find an index I such that both finish of I of that particular process, it is equal to false, and request of that particular process is less than or equal to work. If there is no such I, that is there is no such process exists, then we have to go to step 4. In step 3, we have work is equal to work plus allocation and finish of I is equal to true. So, after assigning this, we have to go to step 2. Then step number 4, again I have to check finish of one particular process is equal to false, and for some I value ranges between 1 and n, then we can say the system is in deadlock state. So, here finish of I is equal to false for some process, then we can say the system is in deadlock state, and finish of I equal to false, then P of I, that particular process is in the deadlock state. Let us take an example. So, in this example, I consider 5 processes P0, P1, P2, P3, P4, and 3 resource types are there, A, B, C, and A is having 7 instances, B is of 2 instances, and C is of 6 instances. So, at time t0, we have the snapshot like this, that is allocation matrix we have like this, we have the request matrix and available. So, here available is at present 0, 0, 0. So, in the allocation matrix we have 0, 1, 0 for A, 2, 0, 0 for P1, 3, 0, 3 for P2, 2, 1, 1 for P3, 0, 0, 2 for P4, and the request is given like this. So, step number 1, work is equal to available. So, we know available is 0, 0, 0. So, work is equal to 0, 0, 0. Then come the next point we have to do, for I is equal to 1 to n. If allocation is not equal to 0, then finish of I is equal to false. Otherwise, finish of I is equal to true. Let us apply to this example. So, for all I is equal to 0, 1, 2, 3, 4, I have to check. I have to check whether allocation is not equal to 0. So, for all the cases, that is finish of 0, finish of 1, finish of 2, finish of 3, finish of 4, all are equal to false. Then step number 2. So, what is step number 2? We have to find an index I such that finish of I is equal to false as well as request of I is less than or equal to work. So, if there is no such I, then I have to go to step 4. Let us apply this step to our example. So, here request of 0, it is 0 0 0 is equal to 0, either less than or equal to 0. So, we have an I, that is 0, process 0. It is existing such that its request is equal to work. So, now what we have to do? We have to go to step 3. So, in step 3, work is modified, that is work is equal to work plus allocation of I, and finish of that particular process is equal to true. So, now I am applying the step. So, work is equal to 0 0 0 plus allocation of 0, and from the example we know allocation of 0 is 0 1 0. So, I have the value 0 1 0 for work. Work is now modified. Finish of 0 becomes true now. So, now I have to go to step 2. So, again in step 2, so already we have completed for 0 process. So, now 1 2 3 4 finish of I is equal to false. So, this is taken away. So, request of 1, that is 202, it is less than or equal to 0 1 0. So, I have, it is not applicable because 202 is not less than or equal to 0 1 0. So, I have to go to the next process, it is 2. So, now request of 2, it is 0 0 0 which is less than or equal to 0 1 0. Yes, this is true. So, there exists an I, that is process number 2 is existing. So, I have to go to step 3. So, again I have to modify work with the allocation of process 2. So, 0 1 0 plus 303. So, now work is 3 1 3 and finish of 2 becomes true. I have to go to step 2. So, now 0 is removed, 2 is also removed from the list. So, now I is 1 3 4. For them the finish of I is equal to false. So, now request of 1, that is 202, it is not equal to or not less than 0 1 0. So, I am moving to this request of 3. So, here 1 0 0, it is less than or equal to 3 1 3. Yes. So, there exists an I, that is process number 3. So, I have to go to step 3. So, here work is equal to 3 1 3 plus allocation of 3, that is 3 1 3 plus 2 1 1. So, the result is 5 2 4 and finish of 3 becomes true. I have to go to step 2. So, now I have removed 3. So, now I, for I 1 and 4 I have to check. So, for request of 1, 202 is less than or equal to 0 1 0. No, it is not correct. So, I am checking for process 4, 0 0 2 is less than or equal to 5 2 4. So, there exists an I 4. So, I have to go to step 3. So, here the work is modified 5 to 4 plus allocation, that is 5 to 6 and finish of 4 becomes true. Then I am going to step number 2. So, now for process 1, this the request is 202 which is less than or equal to 5 to 6. So, I can take this 1. Then I have to go to step 3. Now, work is modified, it becomes 5 3 6, finish of 1 becomes true. Then I have to go to step 2. So, here for all the processes, finish of I is now true. For no process we have the finish value as false. So, we have to go to step 4, where the system is not in deadlock state. For all the processes we have the finish value as true. So, the system is now not in the deadlock state. So, here we can see the sequence P0, P2, P3, P4, P1. So, it will result in finish of I is equal to true for all the processes. So, suppose the request of P2, it is slightly changed, it is sending a new request, that is 001, then we have to check whether system is in the safe state or not. So, let us see. So, initially all the processes we have the finish value as false, then request of 0, it is the value is 000, which is less than the equal to the work. Then I go to the next one. So, now there exists here request of I, request of 1, 202, it is we have to check whether it is less than or equal to 010, no. Then I go to next process, request of 2, it is 001, again this is not correct, that is the condition is not satisfied. Then I go to the next process 100, again this condition is also not satisfied. Then I go to request 4 002, again this condition is also not satisfied. So, there is no I with value finish of I is true. So, for all the processes finish of I is false and the condition is not at all satisfied. So, I have to go to step 4. So, now finish of 1, finish of 2, finish of 3, finish of 4. So, for all these processes the value is equal to false. So, now we can say the system is in the deadlock state and P1, P2, P3, P4 are in the deadlock. So, they cause the reason for the system to be in the deadlock state. Thank you.